Aluminum is one of the most fascinating and versatile metals of the modern world. It's the most abundant metal in the Earth's crust, making up about 8% of its weight, but it's never found in its pure form. Instead, it's extracted from minerals such as bauxite. Thanks to its unique properties, lightness, corrosion resistance, conductivity, and recyclability, aluminum has become a cornerstone of key industries like aerospace, construction, energy, and technology. China leads global production, manufacturing over 50% of the world's aluminum, while countries like Guinea, Australia, and Brazil hold the largest bauxite reserves. Every year, more than 60 million tons of aluminum are produced, and demand keeps rising, driven by the shift toward electric vehicles, renewable energy, and sustainable structures. However, this metal is not easy to obtain. Its production requires massive amounts of energy, which has led to major investments in clean technologies to produce so-called green aluminum. Even more impressive, aluminum can be recycled infinitely, and 75% of all the aluminum ever produced is still in use today, making it a true champion of sustainability. Did you know that recycling just one can saves enough energy to keep a LED bulb shining for 20 hours? Stay until the end to discover how a simple rock is transformed into the incredible metal that powers our modern world. And if you enjoy this kind of content, don't forget to subscribe, like, and share it with someone curious like you. Let's begin our journey to the metallic heart of aluminum. Step 1. Extraction of bauxite, the mother rock of aluminum. The journey of aluminum begins with a mineral called bauxite, a reddish, earthy rock formed through the chemical weathering of aluminum-rich stones in tropical climates. This mineral is the primary source of aluminum worldwide, composed mainly of hydrated aluminum oxides, along with small amounts of iron, silica, and other compounds. The largest bauxite deposits are found in Guinea, Australia, Brazil, and Jamaica, where climate conditions favor its formation and accumulation in vast quantities. Extraction takes place in open-pit mines, using heavy machinery such as excavators and haul trucks, since the ore lies relatively close to the surface. Once extracted, the bauxite is crushed and transported to processing plants, where the industrial transformation begins, separating aluminum from the other materials. Though it may seem simple, this stage is crucial. The quality of the bauxite determines the efficiency and yield of the entire process. And this is where it all begins, a humble, earthy rock that, through an incredible transformation, will become cans, airplanes, windows, or parts of electric cars. The magic is just beginning. Step 2. Refining, extracting alumina through the Bayer process. Once the bauxite is extracted, the next step is to transform it into alumina, aluminum oxide, Al2O3, a white, powdery substance that serves as the foundation for producing metallic aluminum. This stage is known as the Bayer process, developed in 1888 by Carl Bayer, and it remains the most widely used method for refining bauxite around the world. The process begins by crushing the bauxite and mixing it with a hot solution of sodium hydroxide, caustic soda. This mixture dissolves the aluminum compounds within the bauxite, forming a solution known as sodium aluminate liquor. Meanwhile, the unwanted materials, such as iron and silica, are separated as a red, muddy residue called bauxite tailings, or red mud, a byproduct that must be carefully managed due to its environmental impact. After that, the liquor is slowly cooled, and a small amount of alumina seed crystals is added, triggering the precipitation of pure alumina crystals. These crystals are then filtered, washed, and calcined in kilns at temperatures above 1000 degrees Celsius to remove all moisture, resulting in pure alumina, ready for the next stage, electrolysis. This step is crucial in the production chain, since the purity of the alumina directly determines the efficiency and quality of the metallic aluminum that follows. Step 3. Electrolysis, transforming alumina into metallic aluminum, Hall-Héroult process. Once pure alumina is obtained, one of the most fascinating stages begins, turning that white powder into shiny metallic aluminum. This transformation is achieved through a method known as the Hall-Héroult process, invented almost simultaneously in 1886 by Charles Hall in the United States and Paul Héroult in France. This process relies on electrolysis, a technique that uses electricity to break down chemical compounds. In this case, alumina is dissolved in a hot bath of molten cryolite, Na3Al-F6, which lowers the melting point of aluminum and allows the reaction to occur more efficiently. A powerful electric current passes through the bath. At the cathode, the negative electrode, Aluminum ions are reduced and deposited as liquid aluminum at the bottom of the electrolytic cell. Meanwhile, at the anode, the positive electrode, oxygen is released and reacts with the carbon in the anode, forming carbon dioxide. This process consumes huge amounts of electrical energy, which is why many aluminum smelters are built near hydroelectric dams or cheap energy sources. In the end, pure liquid aluminum is obtained, ready to be molded and shaped into countless forms. This is where science quite literally turns into shining metal. Step 4. Casting and shaping the molten aluminum. After obtaining liquid aluminum through the electrolysis process, the next step is to give it shape. This is done through casting and molding, a crucial stage in creating everything from massive industrial parts to small, precise components. The molten aluminum is poured into steel or iron molds, where it cools and solidifies. Depending on the final application, the casting process can vary. For example, in sand casting, molds are crafted manually or with specialized machines, and the molten metal is poured to take the desired shape. This technique is ideal for large or low-volume parts. For high-precision products, such as automotive components or electronic parts, die casting is used, where molten aluminum is injected under high pressure into a closed mold. This method allows for finer details and smoother finishes. Once cooled, the cast aluminum is cut, polished, or further processed, depending on whether it will be used in cans, aircraft components, or construction structures. This stage is essential to ensure the shape, size, and quality of the aluminum meet the exact requirements of its diverse applications. From molten metal to the materials that shape our world, this is where aluminum takes form. Step 5. Rolling, extrusion, and other shaping processes. Once the aluminum has been melted and cast, the next step is to shape it for specific applications. This is achieved through mechanical forming processes such as rolling, extrusion, and forging, which allow the creation of products with different sizes, thicknesses, and structures. Rolling involves passing aluminum through large rollers that flatten and stretch it, reducing its thickness until it becomes thin sheets, like those used to make packaging and beverage cans. The rolling process can be performed hot or cold, depending on the temperature and the desired characteristics of the final material. Extrusion is another key process. Here, molten or heated aluminum is forced through a die to create specific shapes, such as tubes, profiles, and frames. It is widely used in the construction and window frame industries due to its precision and efficiency. Both hot and cold working can be part of the shaping stage, depending on the strength and flexibility required. In some cases, aluminum undergoes heat treatments to improve its mechanical properties, such as hardness and durability. These processes allow aluminum to adapt to a vast range of industries and products, from aircraft components to architectural and decorative elements. From raw metal to refined design, this is how aluminum takes its final form. Step 6. Heat treatments and alloys for the final application. Aluminum is an incredibly versatile metal, but to meet specific requirements for strength, durability, and performance, it undergoes heat treatments and is combined with other metals depending on its final use. These adjustments allow aluminum to adapt to multiple industries and products. Heat treatments include processes such as annealing, quenching, and aging, which improve the metal's mechanical properties. During annealing, aluminum is heated and then cooled slowly to increase its ductility. In quenching, it's heated and then rapidly cooled, which boosts its hardness and strength. On the other hand, alloying involves mixing aluminum with elements like silicon, copper, magnesium, or zinc. These alloys are designed to meet specific needs, for example, higher resistance to wear and corrosion, which is crucial in demanding industries like aerospace and automotive. The type of alloy and heat treatment chosen depends entirely on the final application. For instance, aluminum 2024 and 7075 are preferred in aerospace engineering due to their exceptional strength-to-weight ratio, while aluminum 6061 is widely used in structural and construction applications for its excellent balance of strength and workability. Each alloy and treatment brings aluminum closer to perfection, tailored for every challenge it faces. Step 7. Key applications: cans, airplanes, structures, and more. Aluminum is an essential material across a wide range of industries thanks to its lightweight nature, durability, and corrosion resistance. These unique properties make it a cornerstone in both everyday products and high-tech innovations. In the packaging sector, aluminum is widely used to produce beverage cans, food containers, and foils, due to its ability to protect contents from light, air, and moisture. Soda and beer cans are perfect examples of how aluminum combines functionality and efficiency in modern packaging. In the aerospace industry, aluminum plays a crucial role because of its lightweight structure, which reduces aircraft weight and improves fuel efficiency. Commercial jets from companies like Boeing and Airbus rely heavily on high-strength aluminum alloys to achieve optimal performance and safety. Aluminum is also a key player in construction, particularly in frameworks, facades, and window structures. In the automotive sector, it's used to make vehicles more fuel-efficient by lowering overall weight without sacrificing strength. Even the technology industry depends on aluminum. It's found in electronics, computers, and cooling systems, where its excellent heat dissipation is critical for performance and safety. And that concludes our journey through the fascinating world of aluminum production, from mining bauxite to creating the everyday and industrial products that shape our world. Which step impressed you the most? Tell us in the comments. If you enjoyed this video, don't forget to like, subscribe, and share it with your friends. See you in the next episode, where we'll keep exploring the science that powers our world.